Okay, welcome to the lecture on the mean, the moments, and the variance of random variables. So, just a quick recap, where are we right now? We've learned about three discrete random variables. We've learned about the binomial, the Bernoulli, and the discrete uniform random variables. We've learned what the probability triple is. Recall, it's your sample space, your event space, your probability space, and your support. And the relationship between the support and the probability space, we call that your probability distribution function, or PDF, or P of X, right? And we contrast that from your CDF, or your cumulative distribution function. As your cumulative distribution function tells you the probability that your random variable is equal to or less than that value, right? So the cumulative distribution, tells you what you've accumulated so far. We're going to talk about expectation, right? So expectation has this nice intuitive idea, right? In terms of the distribution, where is the balance point, right? Where is the weight? There's an equal amount of weight on the left and the right. You can look at the probability space. Obviously, it sums to 1. We can look at the expected observations of each face in 60 tries. Obviously, you see 10 of each because they all have 1/6 probability. And then we can accumulate them, right? So we can add up all the 1s, add up all the 2s, add up all the 3s. And then if we did that, and if we toss our die 60 times and did that, we'd expect to see 210 as our total. And then if we divided that by 6, we would get 3.5. And if we use our formula, it's the formula for expectation, which is just the PDF times X across its entire support, right? So that's just going to be 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 and so forth. We add up all those values, and then we get 21/6, which again is 7/2. So there's 3 ways to sort of calculate the expectation, and again, of this instance of the random variable. So remember, we always want to remember this and not get confused here, that this is an instance of the random variable, right? So this is a single die being tossed, but the random variable is just discrete uniform. So the random variable could range from 1 to 100. They just have equal probability. So we're not calculating the expectation of the random variable, but of this instance of the random variable. Right? The mean, or the expectation, I think has more immediate intuition, right? That the average value of a distribution, the middle point, it makes sense that intuitively why we'd want to interrogate our distribution by looking at the average. I mean, constantly we compare the averages of groups, even when we shouldn't. I think intuitively, like looking at the average number makes sense to us. Why variance, and why is that such an important parameter, right? So the first thing is, so intuitively, what are we trying to describe? Well, we're trying to describe how spread out the values are, because we can see that if you're comparing two groups and one has a bigger average than the other, and the value, but the values are really spread out, that might not be meaningful, because if they're really spread out, maybe you need a larger sample. Right? If they're not very spread out, but they're very different, that might be more meaningful. So how spread out the values are is an important thing to know when you are talking about a random variable, right? So one way to think about that is maybe the average distance of a value from the average. So in the table, in the third column, you see that. Of course, in this example, we know our mean of the die is, right, 3.5. But the average distance ends up being 0, right? That's because the small faces of the die have a negative distance, and the large faces have a positive distance. So they equal out, and you get 0. So it's not going to work, right? So we need some way to describe how spread out the values are, where the distances won't cancel. So sometimes you're so you can square the distances and calculate variance. Now intuitively, that makes sense, but why square them? Because it destroys the scale. You could also just take the absolute value, right? So that's what you're saying in the next column, right? You're saying the absolute value of the distance, and we're seeing this, the average absolute value is 3/2. So that's actually not usually talked about in statistics because it's hard to calculate, and there's some other reasons why we like this squared value, but it's very, very useful. And something that, when you're looking at sampling, should always be calculated, right? So we call that the median absolute deviation. Usually it's from the median. In this case, the mean and the median are the same value, so we can just call it MAD. but it's a nice value because it's not in terms of a square, right? It's actually in terms of the distribution. But we can also talk about the variance right here, which is going to be the average square distance away. That way the sign doesn't matter; they're always positive, and it works as well. Also, what's nice about the variance here is we have a nice formula to calculate it. So just like the expectation, we have to sum across our probability distribution, but instead of multiplying by x, now we have to multiply by x minus the average squared. Right? So you can see that there's this sort of same relationship that if you want to calculate the mean, you just multiply by x. If you want to calculate the variance, you multiply by x minus the mean squared, right? Okay, so we just talked about the expectation and the variance on a single instance of a discrete uniform random variable, and that was the instance that describes a single die being tossed. And if you recall, we got 7 halves and 35 halves, right? But we may also want to calculate the expectation and the variance on the random variable directly. So that way, if we see another one, we can just plug in the values and we don't need to calculate it per instance, right? So this is a sensible way to do it, and to do this, we're going to go to our whiteboard and we're going to do the work.
Okay, we're going to calculate the expectation for the discrete uniform random variable. We know that p of x for the discrete uniform random variable is just 1 over n. So we can just pull that out because it does not depend on x. And we can write this. And of course, the sum goes from 1 to n. This is the equivalent of 1 over n times 1 plus 2 plus ... plus n. And we might be familiar with this sequence. When you add up all the natural numbers until n, that sums to n times n plus 1 over 2. Of course, you still have that 1 over n here, so these cancel.
So the answer we got is, n plus 1 over 2. We're just going to see if this checks out, right? So for our single die, which has 6 faces, n equals 6, so 7 over 2 is 3.5, which is what we calculated directly. So this checks out, and we think we did this correctly, right? Okay, now we're going to calculate the variance directly on the discrete uniform random variable. So again, same thing, we're going to go to our whiteboard.
Okay, we want to calculate the variance of the discrete uniform random variable, but we're actually going to do that in 3 steps, right? And in our first step, what we're going to do is we're going to just interrogate this function here, right? So what we're going to say is, okay, why don't we rewrite the variance of x as the expectation of x minus e of x squared. Okay, let's expand that because we remember how to do algebra. Hopefully I do. That the expectation of a value is just the value itself, right? So the expectation of x will be in terms of x, but the expectation of 5 is going to be 5. So the expectation of e of x squared is just e of x squared, because expectation itself is a value. So we can distribute the expectation because expectation is linear. So if we do that, we get e of x squared minus e of x quantity squared. And of course, we see here that there's a name for both of these. So for step 2, we want to calculate, of course, what we still don't know, which is the second moment, or e of x squared. It's going to be really similar to calculating e of x. We're going to pull out our 1 over n, and we're going to get another sequence that looks like this. This is just a sequence of a sum of squares, which we should be able to recall is just n times n plus 1 times 2n plus 1 all over 6, whole thing over 6. And now we know that we're one step closer to calculating variance of x.
Okay, so last step, now that we've calculated the second moment, we know that the variance is going to be the second moment minus the square of the first moment, so we're just going to write these down and we're just going to do some algebra, right?
So from the whiteboard, we have n squared minus 1 over 12. Remember, n is 6 sides of the die, so that ends up being 36 minus 1 over 12, which is 35 twelfths. Again, that checks out. We're going to go back to our whiteboard, spend a little bit more time there.
So one small aside, we've now remarked that we can represent the variance of x as e of x squared minus e of x quantity squared. And of course, we can rewrite the variance as sigma squared, and we can also write the expectation of x quantity squared as mu squared, right? So that's here, and then of course we can rearrange terms. We can also say the expectation of x squared is sigma squared minus mu squared. That's important because what that tells us is that we can go a little farther and we can say, what's the expectation of x1 minus x2, where x1 and x2 are just samples of our random variable, squared. Well, again, we can do our same algebra and we can say, okay, well, that's going to give you e of x1 squared minus the expectation of 2x1 x2 plus the expectation of ex1 squared. Okay, and because we have rewritten our terms here, we can say, well, what's that, right? What's e of x1 squared? Well, any e of x squared is just sigma squared plus mu squared. And then this middle term here, well, what's 2x1 x2? Because expectation is linear, we can pull the 2 out, and of course the expectation of x1 times x2 is just the expectation of x1 times the expectation of x2. What's the expectation of x1? Well, that's the expectation of any sample of a random variable. By definition, the expectation of any sample is just e of x, or mu. So that becomes 2 mu squared. And that's interesting because, of course, we can cancel out these 2 mu squareds with this mu squared and this mu squared, and we're going to get, in total, we're going to get 2 sigma squared. So what that means is that the variance is equal to half of the expected value of the square of the difference between any two random samples. So now we have another interpretation for what variance is.
E of x, right, which is just, f of x times x. We call that the first moment of a random variable. E of x squared, which is just x squared times f of x, the sum of that value. We call that the second moment, and then so forth as the third and the fourth moment. So we notice that, okay, the first moment is the expectation. The variance isn't quite the second moment, but it's related, right? Because the variance is what? It's the second moment minus the square of the first moment, right? So it's similar. And so what we do is we can say, okay, so we can generalize this concept of a moment, and we can say that a moment is just going to be here you see an integral, but that's just think of the integral as a general term for a sum, right? So you see that you have f of x, and then you divide by some constant to normalize, and you subtract some constant c, and you can raise it to some power k. So what is e of x? That's the first moment, and in the case of e of x, well, that's sigma to the k, that's just 1, and the value c is just 0, and k is just 1, right? So if k is 1, c is 0, and sigma to the k is just 1, then you have your first moment, right? So you see here that if your first moment has a lot of meaning, that's the expectation, and what we call the second central moment is the variance, right? So it's the same thing. Again, we don't standardize it, so we don't divide by sigma to the k, or the k is just 0, but we do subtract the mu and we do square it, right? So then if we cube it and subtract mu and we raise sigma to the third power, we get the skewness, right? And if we do that to the fourth power, we get the kurtosis. So the skewness is just basically how off a distribution is from being centered, and kurtosis is a little bit more complex, but just intuitively you can kind of think about it as the distribution not falling down fast, right? So if you have a peak, it's the distribution is going to have sort of fat tails, right? So all four of these things are really nice ways to look at a distribution function. So the motivation to quickly calculate the moments of a random variable is what leads to the development of the moment generating function. So the moment generating function Remember, very similar to the expectation, right, which is just x times f of x. The moment generating function is just e to the tx times f of x. But what's discovered is if you take the first derivative or second derivative or third derivative of the moment generating function, and then you set t equal to 0, well, you get back the first moment, second moment, or third moment, and so forth. So it's a function that when applied to a random variable creates another function which generates moments of the random variable for us, right? So it's a really powerful thing. So real quick, it's not always super easy to calculate the moment generating function. In the case of the discrete uniform random variable, it actually is, right? So here we see how we do this, right? So again, one nice thing about the discrete uniform random variable is you can just pull out the 1 over n, right? Because the probability does not depend on the sum. So we pull that out, and then we see that we have the sum of e to the t xi. You might notice it looks a little bit similar to the sum of a geometric sequence. So to make it the sum of a geometric sequence, we just pull out one of the e to the t's, right? So now we have e to the t xi from 1 to n minus 1. And that actually is a geometric sequence, so we can convert that to the geometric sequence, and we have our moment generating function. So now, to recap, right, we've talked a little bit about the cumulative distribution function. We've talked about what expectation is. We've talked about what the variance is. We've talked about how we can calculate them, right? We can calculate them directly on the instance of a random variable. We can calculate them directly on the random variable itself. Or we can calculate them using a moment generating function for the random variable. So now we're going to go to one of our favorite distributions, the binomial distribution, and we're going to calculate the expectation and the variance two ways. First, we're going to do it on the random variable itself, so directly on the random variable. Then we're going to do it using the moment generating function. So we're going to go to our whiteboard right now, and we're going to calculate the mean of the binomial distribution.
Okay, so to directly calculate the expectation of the binomial random variable, the first thing we do is we notice that this x here means that this sum is not going to actually span from 0, because when x is 0, this sum is going to be 0. So we can just move that up to 1, and then we can factor out this x. So the next step's a little bit tricky. We're going to set m to equal n minus 1, and y to equal x minus 1. Okay, now we're going to see that we can factor out and m plus 1. So of course, if we set a equals p and b equals 1 minus p, then this term here becomes...
Okay, so that was a lot of work, but we've now convinced ourselves that the expectation of the binomial random variable is np. And now we'll do the same thing for the variance.
So like before, that we can also define e of x squared, our second moment, as expectation of x minus 1 plus e of x. Now, of course, we want to calculate this term here. So we can say expectation x minus 1 equals and so if we factor out two lower terms, we now get the sum of from x equals 2 to n. Like before, we can pull out our top terms, and we see, and again, we use the same trick, only this time we're going to have to set our values a little bit different. We're going to have to set y equals x minus 2, and m equals n minus 2. And of course, like before, this value will completely cancel because this is just equal to 1. So that means e of x squared equals n minus 1 p squared. Of course, we still don't have the variance because we've just calculated this term. So we want to now we can substitute this back in. Therefore,
after trips down memory lane into the binomial theorem, we now have shown that the variance of the binomial distribution is np times 1 minus p. Of course, we don't know that from the Bernoulli, so all that work was worth it, or maybe it wasn't, because now we're going to do the same thing on our whiteboard using the moment generating function.
So first, let's just recall the moment generating function for the binomial random variable looks like this. So first step to notice is because we have the number e, we can just rewrite it like this and rewrite as choose k, 1 minus p, n minus k, p, e to the t, whole thing to the k. And of course, this is again the binomial theorem, and we'll break down into 1 minus p plus p e to the t raised to the n. So now we have our moment generating function for the binomial. Next step is to start taking some derivatives. First derivative is going to be n prime t. That's going to just be n p e to the t 1 minus p plus p e to the t n minus 1. And while we're at it, we're just going to take this second derivative. And by the product rule, we're going to write setting t to 0 in the first case, we just get p times 1 minus p plus p to the n minus 1, which is just, of course, np. And, of course, setting the second derivative to 0, we get n minus 1 p squared plus np. And of course, this gives us e to the x squared. If we recall from last time, that n minus 1 p squared plus np plus np squared p1 minus p, and that's the variance.
So that's a little easier, right? So we've already seen the benefits to the moment generating function. Can make your life a lot easier sometimes, right? Also really helpful for characterizing distributions, which we're going to get into in the future. So, done a lot of work now. We're starting to get good at this, hopefully. And we're going to just review the topics, and of course the homework for this lecture is included in the homework section of the folder. So to summarize what we learned about the cumulative distribution function. We learned about the expectation of a random variable. It's linear. That's important. We learned about the variance of the random variable, and we learned a really important formula, right? We learned that the variance is just the expectation of x squared minus the expectation of x squared, right? And we also learned that, again, I think also really interesting and really useful, is that the variance is twice as large as the expected square difference between two random samples of a random variable. We learned about the moment generating function, how to use it. We learned a little bit about the higher moments. And just to kind of recap what we now know how to do, right? We know how to calculate the expectation and the variance directly on the instance of a random variable. And we can do that either by hand, or we can do that with our computer simulation, which we did in our first lecture in Python, right? We also realized that we can just calculate it directly, just analytically by hand, again, but on the random variable itself. And then we get a formula which we can use for all instances. We also learned that in cases like the binomial, where that's really hard, we have this other tool now, this moment generating function, that we can also use to calculate the moments, which then can pretty easily be used to calculate the variance and the expectation. So that's the lecture. Looking forward to the future. Next week we will be wrapping up the discrete random variables. So everybody will at least have a favorite discrete random variable by next week. So keep thinking about what's your favorite one. It's only 3 right now, so we're probably going to get about 3 more that we'll cover, and we can choose a favorite then. And then beyond that, we're going to move into the continuous random variables, and then finally sampling and whatever everybody wants to do, data analysis, right? So we're getting there. Just stay strong, and it gets easier.